Hello, students. I hope you're staying dry. Is the audio coming through? Did
Yes.
everybody hear me? Thank you. Let me test.
Yes.
Thank you. That's always comforting when everybody chimes in with that. Sometimes when I ask, people are just too shy. Don't be shy about math. Enjoy, and it does help to hear me. Like I said, even though it is a more Southern accent, um, it's not a Texan accent. Since I grew up in North Carolina, it's a little bit different. A lot of individuals say there's more of a drawl to it. But I guess maybe when I was a little tyke, I had more of that because everybody around me spoke that way. But what I want to do today is to cover the remaining material basically on the theory of equations, so we can complete that. And then on Thursday, spend some time with the rational functions and the asymptotes and the fun stuff that you did back in college algebra. And then, of course, I just want to make you aware there's a 3.7 section, which I really won't lecture much on. It's just more problems with the BD technique with the inequalities. Dr. Stewart provides another section of that in chapter 3, and you use the same techniques that you already know from what we did in chapter 1. So just use that as some additional practice. It's not new material, it's just some extra practice with the inequalities that I think will be very helpful when you get to calculus. Now, what I want to do is start out with the, let's see if I can find this. Let's see here. What does this look like? Let me find the mind tab. And let's see. Okay, that's where that is. Okay, let me see what I have here. So, okay. Now, what I want to show you here is where we left off last time. Remember, we had the rational zeros theorem. And I just want to remind you of that. And what I'm using is your ebook from your text that you use in WebAssign. And I just want to remind you of that. And then I want us to maybe incorporate it into a couple of problems when we need it. I just want to remind you that sometimes all you need is factoring, which we already really pretty much know how to do. When you've got a basic factoring technique, continue to use that because that'll probably make for a quicker solution. But you always have many ways to look at problems. Now, I just want to remind you that we start out with a polynomial in the standard form. Remember, we had the a sub n, x to the n, and we decrease, that is in decreasing form, down to the x term and then the constant term. And when we apply rational zeros, we're always assuming that the leading coefficient is non-zero because that gives the degree of the polynomial. And then, of course, in this case, the a sub 0, which is the constant term, we're assuming is non-zero. If that's not there, if it's a 0, then we know x is a 0, and then we can just factor the x and start over again. Now, what I said last week, and the theorem statement doesn't clearly address this, but you know this is true. We're going to write the fractions as p over q. And we're going to make the assumption that p and q are relatively prime in the sense that they have no other positive common factors except for 1, like maybe, 5 over 1, 2 over 3, 1/2, things like that. And then the beauty of the theorem is that the p in the numerator will divide the constant term of the polynomial, and the q in the denominator will divide the leading coefficient. So like I said before, this is a problem that we can work backwards. So before I do a factoring problem to remind you where we've been, I'm going to go ahead and apply the rational zeros theorem so you won't think I'm just wasting your time. So let me go ahead and share my screen for that. Now, like I said before, if you can see a really nice factoring method like a quadratic form or even maybe the binomial theorem, then use it. But here's an example from your WebAssign where we have p of x equals 2x to the fourth. And again, all of these are going to be integer polynomials, ladies and gentlemen. When we apply the rational zeros theorem, the coefficients must be integers. And that's what we stick with mostly in this class anyway. But we can get creative, and you will certainly see that in your other classes, your engineering classes and your science classes. Now, when we look at this problem, what we want to do is determine zeros, as we always do, and factor. And what the goal today is going to be a complete factorization, like you have when you talk about the fundamental theorem of algebra, complete factorization. Where if we have to, we jump into the realm of the imaginary numbers so we can get all the zeros. Now, to remind you, this is how we're proceeding with all of these problems. We have a degree 4 here. So from the fundamental theorem of algebra, we know there's at least 1 zero, but by complete factorization, there will be 4. Now, this is why it's important to remember repetitions, because the complete factorization includes repetitions. Maybe you have 4 zeros, but they're all the same. Maybe you have 4 zeros, but in pairs, they're the same. That is, you get 2 3s and 2 5s or something. So remember, the complete factorization includes repetitions. So we don't think of you know, x plus 4 raised to the 4th power as being 1 0. That's 4 zeros that repeats 4 times. So that repetition is really important. So don't forget about that, please. Now, let's notice here, we can go ahead and notice that this is an integer polynomial. So I'm using the sign for z for integers. And we have a constant term right here. So that'll be a sub 0 is negative 32. And we have a leading coefficient, which is 2. So that will be a sub 4 equals 2. Now remember, I'm going to use a little notation here. The p, it'll be a vertical line. That means divide. P will divide negative 32. That is, p is a factor of negative 32 from the theorem if it is going to be a rational zero, and q divides 2. That's just a shorthand notation that will save you a little bit of time when you're thinking about writing the candidate list. So like I said, we're going to use this theorem backwards to figure out what the zeros are. So now we'll say p divided by q. And we're going to put all the factors of 32, but that's really easy because that's just 2 to the 5th. So good for WebAssign. Plus or minus 1, plus or minus 2, plus or minus 4. Just go in factors of 2, plus or minus 8, plus or minus 16, and plus or minus 32. We don't really even have to worry about the prime factorization because, like I say, that's 2 to the 5th and we cover everything. And now with 2, we can get plus or minus 1 or plus or minus 2 in the sense that these would be the possible divisors of 2. Now, what kind of list does this give us? Well, now remember, if the WebAssign problem says just give the candidate list, you'll have to write all of these separately. You can't normally use the plus or minus. You'd have to like do 1 and then minus 1 in a separate type list. I don't usually think the WebAssign likes the plus / minus symbol. Now, so we've got what? Plus or, if we divide everything by plus or minus 1, we have plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Obviously, most of these are no good, but that's how we proceed with this, plus or minus 16 and plus or minus 32. And then if we divide by 2, this is not a problem. Divide by 2 here, we get 1, 2 here, 4, 8, and then 16. So that's already in the list. So the only new one will be the plus or minus 1/2. So again, if you were doing just a list, you'd have to do 1, minus 1, 2, minus 2, 4, minus 4, 8, minus 8, 16, minus 16, 32, minus 32, 1/2, and a negative 1/2. So you might have a problem where they ask you just to give the candidate list and not check anything. Now, when we look at this particular problem, we think about the fact that WebAssign has set this up and they're trying to test us on the rational zeros theorem. So first, what we want to do is to draw the little table to get everything started. Because remember, we can use synthetic when we divide by x minus c, or just test that c is actually a 0. So we put our coefficients here in descending order: 2, negative 13, 6, 64, and negative 32. Now, one thing that we can notice here, and this is important when you're doing this, you want to start with small numbers to give yourself a break. But if we look here, we can look at these coefficients and make a note here. When you add here, you get 70, you got 72. So these numbers do not sum to 0. So there's no need to worry about checking 1. I mean, if 1 works, it's pretty obvious. So we're going to bump up the 2 and look 2 and 4, and then try to think about the bounds theorem that you learned about in college algebra to figure out if we need to keep going. And I'll say more about that as we work into this. So we're going to start with 2. So bring the 2 down. 2 times 2 is 4, and we add that to negative 13 and get a negative 9. And that's the process. Then we have 2 times negative 9 is negative 18. So a negative 18 plus a 6, that'll give us a negative 12. Now we continue the process again. 2 times the negative 12 is a negative 24. And we add that to the 64, and that'll give us a 40. So these computations are relatively straightforward. And then we have a 2 times a 40, which is an 80. And then, of course, we subtract 30 and get 50, and then another 2 gives us a 48. So what we can see, at least from doing this, is that 2 is not a 0. But remember, the bounds theorem says that if this row exists of non-negative entries, like positive numbers and 0, then you don't need to keep going to check numbers bigger than 2. But we've got negatives here, so there's no reason to think that we shouldn't try some other candidates from this list that are bigger than 2. Again, if these were all positive, then we'd be wasting our time, because you can't add a bunch of positive numbers and ever get 0. So let's go to the next element of the list, which is 4. So we'll try 4. And if we hit the jackpot, then we'll do another table for the lesser degree polynomial. So bring the 2 down. 2 times 4 is 8, and we add 8 to negative 13, and we get a negative 5. And then 4 times negative 5 is negative 20, and we add a 6, we get a negative 14. And then we keep going. We have a 4 times a 4, that's a 16. Add 1 to 4, that gives us a 56, negative 56, and we add the 64, so that'll give us a positive 8. And then we have 4 times 8, which is 32. If we add the negative 32, that gives us a 0. Now, the thing about this is that we can still keep charting along in this direction, but we found a 0. So that means this is going to say, okay, if we have a 0 remainder, then 4 is a 0, and then this implies that x minus 4 must be a factor. So we're doing the factor theorem in reverse, since we're not building the polynomial. So x minus 4, and then here's our reduced polynomial of degree 3. So we have 2x cubed minus 5x squared minus 14x plus an 8. Now, again, we're done with this table, and we've got a new polynomial to consider. Now I'll make this comment. This is degree 3. It's not quadratic, so we can't use our theory for the quadratic equation, and it's certainly not quadratic form. So what we want to do is consider other rational zeros here. Again, in this case, the constant term is 8, and the leading coefficient, that'll be a sub 3 now, is 2. So we can do, again, p divides 8. And this is nice because we like these powers of 2. It makes our work a lot easier. And p divides, q divides 2. So we can get a list. So the factors of 8 plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. And then, of course, 2, we get the same thing, plus or minus 1, plus or minus 2. Now, what we can notice here is that when you consider this, we're at the same point we are here. So we can go ahead and write a list. Divide everything by plus or minus 1. We just get plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. And then by the same token, if we divide all these by 2, then we get the 1, the 2, and the 4. So we're done. We've already got those right here, but then the 1/2, again, is something new. So we can do another table. So hopefully we can reduce to a quadratic polynomial. So let's go ahead and put our descending coefficients. 2, -5, -14, 8. Now again, we can do the same kind of check that we did before. Notice here that we get a 10, and here we get a -19. So 1 clearly doesn't work. And notice here that when we look at this particular problem here, so we know 1 doesn't work, and we've got negatives here. So there's no reason to think that 2 or 4 might not be good candidates again. So let's do the same thing we did up here. Let's try the 2. See if maybe we get a 0 of 2. Bring the 2 down. 2 times 2 is 4. 4 plus a -5 is a -1. Do it again. 2 times -1 is a -2, plus a -14, that's a -16. And then, well, that's not going to work. 2 times -16 is a -32, plus an 8, that gives us a -24. So that didn't work, but it doesn't say that we should stop. We've got some negative entries here. So we're kind of like at the same place we were here. Let's try the next number in the list, which is 4. Always start small. Don't start with big numbers. That's too much work. Start with the smaller, give yourself a break. So now we bring the 2 down. And again, you want to start with numbers that are realizable to get the flow of the problem moving. So 2 times 4 is 8. 8 plus a -5 is 3. Let's do the process again. 4 times 3 is 12. 12 plus a -14 is a -2. Well, this is going to work. 4 times -2 is -8. Plus 8 is 0. So we're like we got here. We've got a double root, at least right now. So this implies if we have a remainder of 0, that 4 is a 0, and x minus 4 must be a factor. So we have p of x. We can go ahead here. We have x minus 4. And now for this, we have x minus 4. And then the reduced polynomial right here, 2x squared plus 3x minus 2. This is why we add without putting the numbers in the table, because we want the rows here to make sense to us. I mean, you can do that, but then you've got rows that aren't going to really tell you anything, but that's your choice. Now we look at this and say, okay, well, this is quadratic, so we're done with the rational zeros. We don't have to do that. We understand quadratics completely. We can use the quadratic formula, we can factor, we can complete the square. We don't need anything but what we know about the quadratic formula. So you never have to use this for quadratics. So let's check here. It looks like this will factor, or let's at least try. Let's look at AC. So we get 2 times the negative 2, that's a negative 4. And so we know what we need to do. We need the sum to be 3. So let's just write that as a 4 times a negative 1. And that'll give us the z and the w whose sum is 3. So that was pretty straightforward. So now let's go ahead and factor. So now we're doing complete linearization. So let's go ahead and write these separately. You can square it if you want, but I want to make the point that we now have 2 zeros. They're both the same, but we still have 2 zeros. And so we have 2x squared plus 4x minus x minus 2. So this gives us x minus 4, x minus 4. And now we can factor by grouping. So this is going to give us a 2x times an x plus a 2. And then if we factor, in this case, the negative 1, we can say plus negative 1 times x plus 2. And so now the x plus 2 multiplies the 2x and the minus 1. So we get x minus 4. Let me move this up a little bit. X minus 4. And then we get x plus 2 times 2x minus 1. Now, WebAssign doesn't care how you write your factorizations. Normally, they might say, well, I would like you to write it as an integer factorization. You could stop there. But that kind of defeats the purpose. So I think the WebAssign's smarter than we are. And that's not a surprise. The WebAssign is such a magnificent tool. My colleague Nate works a lot with artificial intelligence, and it is pretty smart. So if we look here, we can think, let's just go ahead and expose the 0 by factoring the 2 from this factor. Let's just take the 2 out. So 2, x minus 4, x minus 4, and then x plus 2, and then that'll leave us with an x, and then divide by 2 minus a 1/2. Now, what we've done here, except, and this is kind of overkill, you don't always have to do the minus minus, but if you like, let me just make a point here, just to kind of do it, even though WebAssign would think this is more than good. Let me just go ahead and write this with all the minus signs, so we have a nice example of complete factorization. So I'm going to do minus a negative. So when we look at this kind of kills 2 birds with 1 stone. Notice here, the leading coefficient is 2. And so when you do complete factorization, the 2 is factored, and then you get all of the zeros, x minus C1, x minus C2, x minus C3, x minus C4. So we can write this in general as an A, where that would be like the A sub 4. And we have x minus C1, x minus C2. Well, these could be real or imaginary. We just call these complex numbers because they include all kinds of numbers, all the numbers that we work with. So if you go ahead and start getting used to the complete factorization, that's probably better, even in 3.4, and then use it in 3.5. The beauty of this is that this is the goal of the fundamental theorem of algebra. From the fundamental theorem, we can always do this, even though in some cases, ladies and gentlemen, it might be really hard to do this. It may be hard to find the zeros, and we may have to do some calculus and approximate them. So formulas, and all that like this are not always something that we can write, but since we have a 4th degree polynomial, we know that there are 4 zeros. And even if we have repetitions, we count the repetitions. So this has multiplicity 2, but the 0, negative 2, and 1/2 have multiplicity 1. So we could write our zeros right here. So if WebAssign said, list the zeros, you'll be 4, 4. So we have here 4, 4, negative 2, 1/2. And always remember the repetitions. I know multiplicities are hard to get used to. So now we think of the repetition as counting as that many zeros. Even if the zero is repeated, that's okay. They still, in this case, that counts as the two fours count as two zeros. That's a zero, that's a zero for a total of four. So the goal in 3-4 and 3-5, and even in calculus, is complete factorization. Because here we just pick it off. We just pick off the zeros. We write, and if we need to do a sign test, this is tailor-made for the sign test. We can't do a good sign test, ladies and gentlemen, if our equations are messy. They need to be clean and they need to be user-friendly. So what I want you to see here is that this is a really good candidate for the rational zeros theorem, because we start out with a integer polynomial and it doesn't really fit any pattern or factorization method that we've done before. So we find out that this tool is really good, but beware. Even though we generate a list, it doesn't mean that we have rational zeros. Maybe none of them work. That's usually not what Professor Ron does to his students, and WebAssign has no intention of doing that either. They will give you problems where you might have a couple of rational zeros and then maybe a couple of imaginary or maybe a couple of irrational, just to mix it up. But the whole idea is we want you to get accustomed to using the rational zeros theorem and feeling some confidence that you actually find some. But you might be working an engineering problem and maybe you've got maybe 6 or 8 candidates in the list and none of them work. And so you've got to approximate your zeros. None of them are rational, so you're going to have to do some calculus to approximate, or take out a fancy calculator that plots 1,000 points. But that's really not any good because that's cheating. But I guess once you get your engineering degree, you can use whatever software you like. Now, what I want to do is do an example that doesn't really require rational zeros, but just to remind you where we've been. This was a WebAssign problem, and what they do is they place it in a section where you think you might have to use rational zeros. And I want to show you that you have options. So here's an example. We want to do the same thing, find the zeros and completely factor. So we have x cubed, again, this has a leading coefficient of 1, plus 12x squared, plus 48x, plus 64. So basically here we want a complete factorization, and that means finding the zeros. Now, what I want to impress upon you here is that we got this 64, but that's just powers of 2. And we're like, okay, well, we've been there before, Professor Ron. What are you talking about here? What are you noticing here? Well, notice, everyone, this is a perfect cube, and that's a perfect cube. This is just x to the third. This is binomial, and this is 4 to the third. And you're thinking, are these the middle terms of the binomial expansion when the n is equal to 3? Well, let's check. Remember from before, we had a plus b quantity cubed equals a cubed. This was an identity from the first day, plus 3a squared b plus 3ab squared plus b cubed. And so now we can see a equals x, b equals 4. So if we fill everything in, let's see if we actually get a factorization for cheap. So we get x cubed plus 3x squared times b, so that's a 4, plus 3 times x times 4 squared, that's a 16, plus obviously 64 here. But now we see that gives us these terms, the 3 times the 4, so we get x cubed plus 12x squared plus, and then of course the 3 times the 16 is a 48 plus a 64. So we got that one for free. Now we could have tried the rational zeros theorem. It probably would have, taken a little more time, maybe not so much, but this is just what? X plus 4 to the third power. So we have three zeros as we expect, but they're a repetition of -4. So we have zeros. So you could write this like this: X. Well, this would be beating it up. WebAssign is fine with this, or you can do the complete linearization and make a note of all the zeros. I'm just doing this to emphasize the fact that you can always do this. And we've got the 1 out front, which is kind of the token 1. So here, all the C1, the C2, and the C3 are all -4. So we say zeros -4, comma -4, comma -4. And there's our factorization right there, which is completely fine. Or if you just want to remind yourself that this is what we have, if they were all distinct, we would have to go this route. But again, this is the A, X minus C1, X minus C2, X minus C3. Now, like I said, WebAssign is not picky about how you factor. They're not worried that you give them an integer polynomial if you start with 1. If you've got some fractions around or whatever, that's okay. They don't specify. I looked through all the formatting and it's really nice. And I played around a little bit with it. And I said, yeah, WebAssign's actually saying I'm giving you flexibility with these problems. But of course, you wouldn't need to do this. I'm just trying to make the point here that this is always possible. And even though it's overkill, when you compare it to the last one, we see we're doing the same thing here. The C1, the C2, the C3, the C4. Okay? Now, one thing that actually is kind of interesting here is we've got some nice properties that I want to tell you about. And before we do that, I actually want to do one more example with the rational zeros. Then we'll talk about Descartes and the bounds theorem, which I've already let the cat out of the bag with that anyway, but we'll do it. I just want to give us a little bit more practice with rational zeros. You probably got too much of this in college algebra, so if this is boring, I'm sorry, but I want to make sure that everybody gets this. This is important, ladies and gentlemen. When you get to calculus, I see that students cannot do this. And this is important that you have these techniques. So for instance, here's another example. We want to do the complete factorization. So P of X equals X to the 4th minus 9x cubed plus 24x squared minus 9x minus a 27. Now, again, WebAssign was pretty good to us, but when we look at this, that's a perfect cube, that's a perfect 4th. We don't get all of the nice pattern that we got in the last problem where we could cheat with an identity using the binomial theorem. So here we really do need to look at the rational zeros to see if we can find some. So we want a complete factorization. Even if it doesn't say that, WebAssign is fine if you do it, okay? It's fine, do it. Get practice with this. So notice here, the constant term is -27. Those are just powers of 3. And then the leading coefficient, well, that's nice. A sub 4 is just 1. Well, that's a gift. You can see that when the numbers get relatively large with lots of factors, this theorem is a little bit tedious. But what we want to see is that as you learn, some of you learn some coding, you may already know this, you can actually write codes to check rational zeros to save yourself time. I mean, that's always fun. Computer programming was something I've always enjoyed. And when I do LaTeX programming, it's the same thing. But so give yourself some opportunity to take some computer science if you can fit it into your schedule. I think you'll enjoy it. Now, we look for the fact that P must divide -27 and Q must divide 1. So we just have powers of 3 here. So we have plus or minus 1. Well, we start out with plus or minus 1, then plus or minus 3, plus or minus 9, and plus or minus 27. Now, again, in the denominator, we're good to go. So it's funny, the list here is easy. Plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 27. The goal here is not to rack your brain with a lot of tedious arithmetic. What I want you to do is gain facility with this and know that you have it to use when you do physics and engineering problems. So again, we can go ahead and use our synthetic table. So we have 1, -9, 24, -9, and -27. And now, of course, we can do the same song and dance we did before. That's a -36 and then a -45 if you add up all the negatives. And when you add the positives here, you don't get 0. So there's no need to check 1. Sometimes students will just check 1, and that's a waste of time. You can scan the coefficients and know, don't waste your time with that. Now, the next number, again, we've got some negative coefficients here, so there's no reason to think that we shouldn't try 3. So let's try 3. So bring the 1 down. 1 times 3 is 3. 3 plus -9 is -6. Now we have 3 times the -6, which is a -18. Add to 24, that gives us 6. And now, if you will, 3 times 6 is 18. We add a -9, that gives us 9. And then you can see this is actually going to work. 3 times 9 is 27 plus the -27. So we actually do get a 0 in 3. So this implies, by the factor theorem, that P of X is X minus 3. And then we have our reduced polynomial of degree 3, 1 less than this. X cubed minus 6x squared plus 6x plus 9. Now, what's interesting about this polynomial, even though it's not binomial, you can look at this and see, well, first of all, you know, 1 is not a 0, but we're going to do the same thing we did before. We're going to generate a list and we're going to try 3 because that looks very promising for 3. So here we can say the constant term here is 9. The leading coefficient is 1. So we'll do the ace of 3 is 1. So we have P over Q. Remember, P divides 9 and Q divides 1. So we get plus or minus 1, plus or minus 3, plus or minus 9 divided by plus or minus 1. So the list, again, if there is a rational 0, it must be in this list. This is the theorem in reverse. Plus or minus 1, plus or minus 3, plus or minus 9. So we can do another table. See, we always want to move to a new table so we can get the new reduced polynomial. Otherwise, you're defeating the purposes of doing this. So now we have what? What's our decreasing? You know, our coefficients in descending order. 1, -6, 6, 9, and we've already cast out 1. So let's try 3. So 1 times 3 is 3. 3 plus -6 is a -3. And then 3 times -3 is -9. Plus 6 is -3. And like we thought, it does work. 3 times -3 is -9. Plus 9 is 0. So we get another 0 in 3. So actually a double root. So this implies is reduced. So we have P of X equals, well, right here, we start with X minus 3. And now we can rewrite this using this information. We get another X minus 3 and then our reduced polynomial, which now will be what? Quadratic. X squared minus 3x minus 3. Now, I think what's important here, and what's important about doing this is that the goal, if you start out with cubic, is keep your fingers crossed for a rational zero so you get a quadratic, and then you're home free. With the fourth degree, keep your fingers crossed that you can get 2 rational zeros, then you have a quadratic, then you're good to go. So the idea, we spend all of this time on quadratics for a reason, because it's really the only polynomial that gives us any relief at all. The rest do not. I mean, of course, linear, but cubic, quartic, quintic, all of the, it's a nightmare. So the idea is what we want to do is focus on getting this. Now, if you look at this being a quadratic, you're thinking, well, we could try Professor Ron's lemma, but notice here, we have AC will be 1 times a negative 3. And so we're thinking, can we rig it so that the factors add to negative 3? Well, no, not really. There's not really anything we can do with this. We can move the negative around and we still are never going to get a negative 3. So this doesn't work. So unsuccessful. So what we can do is say that it probably is the case that the zeros are irrational, if not, well, you can tell, imaginary. So again, how do we start the quadratic formula? We do the discriminant first. Just to remind you, remember, and everybody forgets this, and I forget that sometimes you all are in overload. Remember, that's the opposite of b plus or minus the square root of b squared minus 4ac divided by 2a. So we want to use this, but remember, Professor Ron's method is to do the discriminant first so we don't fill this up with too many numbers. So b squared minus 4ac. Okay, so we've got a b, which is a negative 3, squared, minus 4. We have an a, which is 1, and we have a c, which is, in this case, a negative 3. So this gives us, in this particular case, we get a 9 minus minus plus a 12. So we get irrational, but they're not imaginary. So this gives us 21, which is positive. So this implies 2 distinct real zeros. So now we can use the fact that we don't have to start over with this. If you start out with the quadratic polynomial, you don't have to do any of this. You go right to this. That's all you need to do. And if it's in quadratic form, even better. Quadratic form is great. You can factor it. I mean, the quadratic form is your friend. And when you spot it in a physics class or engineering class or whatever, use it. Now we can fill everything in. X equals the opposite of b, so that's 3 plus or minus the square root of the discriminant, which is 21 square root, divided by 2a, which is 2. So now we can write all the zeros down. And we can write our 0 here when you type this into WebAssign as a fraction to get that nice linearized form, that nice complete factorization. So zeros. So we're seeing that the rational zeros theorem can come in very handy. So if we go back up here, we've got 2 3s, so repeat 3, 3, and then we've got the plus radical, 3 plus square root 21 over 2, and then 3 minus square root 21 over 2. So those are our zeros. And note, the leading coefficient is 1, so the a on the outside is just a shadow 1 anyway. So now we can do complete factorization. P of x will be x minus 3, x minus 3, and x minus the first one, 3. Use your fraction bar, use your WebAssign fraction bar, just like that. No parentheses, just use the fraction. WebAssign understands what it is. It's completely clear what we mean by that. Part of doing math is expressing yourself correctly. And I know that's frustrating, but you want to be a STEM professional and you want to keep your job. So the idea is that you have to be very concerted about how you state things so that your colleagues understand what's going on. I mean, when I had to take exams as a graduate student and defend a thesis and things of that nature, you know, you sink or swim. And you have to convince the people with whom you work and the people that you're trying to convince that you have authority about what you're doing. They don't expect you to be perfect, but again, take care when you write your mathematics. We all want to be like computers, but that's not possible. But we strive to do our best. And so our last one here will be 3 minus square root 21 over 2. So now notice, the 1 is just hanging out right here. We have x minus c1, x minus c2, x minus c3, and x minus c1. So this will give you practice with the complete factorization, which you can do throughout these sections. And what's nice about this, again, is that we utilize the rational zeros to find, if they exist, some rational zeros. We know they have to exist in these lists. When the lists aren't too big, the task is not that difficult. And then we reduce to a quadratic, and we have an equation here that we completely understand. So the idea here is that we check for Professor Ron's AC lemma. Didn't seem to give us anything. We look to the quadratic formula, and we have 2 distinct real zeros to add to our list here and here. And then, of course, the factorization that we have here. Now, what I want to talk about is, I've been mentioning something about the bounds theorem. So I just want to look at an example where we kind of work backwards and verify it, because it's not extremely robust, but I may actually end up using this one as an example. So hold on to that idea. We may come back with that. So let me go back to my screen here and just give you a little summary from your ebook of the well, first, before let's see, what's the best thing to do? Let's do the Descartes, then the bounds. They're all connected. So let's see here. Yeah, we can do the Descartes. And let me move Professor Ron over a little bit. Bye, Professor Ron. Okay, here we go. Yeah, I have to move myself over because my screen, it just gets kind of tiny, so I can't really see myself, but I know you all can. Not that that's any good. Okay, now look at this, everybody. This is called the Descartes rule of signs. Now, why do we care about this, and why do we even care about the bounds theorem? I want to just kind of read through this, and then I want to show you how to do the variation in sign, okay? So again, notice here, we want to have a polynomial with real coefficients, okay? When I say real coefficients, just like what we've been working with. And then if we're looking for the number of positive zeros, of a polynomial, we're trying to find the possible cases here. We look at the number of variations in sign of P of X, or we look at a number that is less than that by 2, an even whole number, or some multiple of 2. Okay, and then we might say, well, what are the possible cases for negative real zeros? For instance, if we have negative zeros of P, how can we figure out how many we may have? Well, we look at the number of variations in sign. That is, this number is equal to the variation in sign of P of negative X. That's the reflection of the graph of P in the y-axis. Or it's equal to that number or less by an even whole number, less by some multiple of 2. Now, that sounds a little bit complicated, but let me show you how simple it is. It is a major result that I actually proved for a seminar. This is, gosh, when I pretty much started, like about 8 years ago. And I had to make sure my students knew some calculus because we had to use Rawls theorem and a lot of number theory. But let me show you in this particular problem that we just did how this will work out. So we're going to go back to this problem and use this as an example for Descartes. So we have x to the fourth minus 9x cubed plus 24x squared. I knew there was a reason I did this one. Minus 9x minus 27. Now, the variation, I call it VAR, variation of P of x. This will keep track of the number of positive zeros. So what we do is we start at the dominant term, we start out positive, then we have a change. So there's 1, another change, that's 2, another change, that's 3, and then it stays the same. So watch this. We start positive, then we go negative, 1 change, 2, 3. So we have 3 variations in the signs of the coefficients. That's how you do variation. And you're thinking, how did Descartes figure this out? It's a really magnificent result, but again, it doesn't have as much play with students anymore because of technology, but it's still an important result and can actually help you out quite a bit. And then now we say if we're doing WebAssign, we could say that the positive zeros, the number could be 3, or we could decrease by 2 to get 1. And then you're thinking, when do you stop? Well, if you subtract another 2, you get a negative number, and that makes no sense. So we've got the possibility of 3 positive zeros or 1 positive zero. Okay, what about the negative ones? Well, we look at the variation of P of negative x. Now, lots of times, ladies and gentlemen, you can do this basically just by staring at it. But let me show you what we do just to give you some practice, because you know the evens will absorb the negative and the odds will retain it. So just some practice. Negative x to the fourth minus 9 negative x, or additive inverse, to the third plus 24 negative x squared minus 9 additive inverse, or negative, however, minus 27. So again, we know by the transformations that this is simply a way to reflect the graph in the y-axis. So you could see when you prove this, you wouldn't have to do it over for this case. You would just flip this into this previous case. So the key with a lot of theorems in mathematics is that even though you get a twofer in the result, you only have to really validate one of them, because you can morph this into that one, but more on that later if you're interested. So now the negative gets absorbed by the 4, so we get x to the 4th. And now, of course, it survives here, so we get a negative times a negative, so we get plus 9x cubed. Now, of course, here it absorbs, so we get plus 24x squared. Now, of course, it's just negative to the first power, so negative times a negative, we get positive. And then we have the negative 27, which is just fixed. Okay, so now when we look at the variation of P of the negative of x, we're thinking, okay, let's start here with positive, 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 1 change right there, 1. So now when we look at negative zeros, how many negative zeros could we possibly have? 1. Now, what I want to do is show you how this would make any sense if you were working a problem. Well, then you would say, okay, well, I could do positive, I could do negative, and I know it's 4th degree, and maybe I could have some imaginary. But the thing about the imaginary with the real polynomials is that they have to occur in conjugate pairs because of the quadratic formula, plus or minus, complex conjugate pairs. So we think, okay, well, that's important. So we remind ourselves of that. So say if we had 3 positive zeros, we could follow this and get 1, because that would be a case, and then no imaginary. And then, you know, we could look at the situation where, for instance, if we had, you know, and this is, I guess this is an important idea here. When you think about this case here, you're thinking, well, we could have 1 positive 0, and then to ensure that we have an even number here, we'll go 1, 1, 1, 1, and then 2 imaginary. So this would be a possible distribution of zeros for this particular polynomial. So we could have this, or we could have this, but let's just go right back to this problem and write down the actual zeros. We have what? 3 plus square root 21 over 2, and 3 minus square root 21 over 2. Well, we don't have any imaginary, so this one does not occur, But the only other one is the one that actually does occur. We have 3 positives right there and 1 negative. So this one is what happens right there. So if you were doing a problem and you didn't have any success, with the rational zeros theorem, and you did Descartes, and you said, well, one of these has to be the case. So this could help you if you had, you know, were checking some numbers or had some technology. You could say, well, let me check around here. This is restrictive, and so this would kind of give you some way to look more clearly. Say you have some other ideas that you want to bring into the mix. So the Descartes just basically says you could have this or you could have this. And if you had done, for instance, the rational zeros theorem, and you already had this right here, then you could already rule this out and go straight to this one. So the beauty of this is that you can do a little bit of work, and then you can eliminate one of the cases and say, okay, this is the case that we have. So the Descartes rule of signs is basically a theoretical result that tells you how you can distribute positive and negative zeros. And then, because these are real polynomials, you know that if you have any imaginary zeros, they must occur in pairs. So in even numbers, like you could have 4 or 2 or 0, where 0 is kind of like the quasi-even number. So the idea with the Descartes is that it supplies conditions and scenarios for how the positive and negative zeros can be distributed. And then of course we can tack on the imaginary just because we can. All right. So I want you to be aware of the variation as we've done here. It's very simple, but you have to be very careful when you do this, that you obey the absorb with the even, and then the retain with the odd. So just remember that, just like the signs that we use when we do sign tests for inequalities. Now, there's another example that I have here that I want to share with you. It's the bounds theorem, and we can use an example that we haven't done yet. Now, this bounds theorem I've already alluded to. Remember when I said we had negative entries? We kept trying bigger zeros because it made sense. Well, now I want to share with you a result that alludes to that. So let me share it. Let's go back to your ebook. And we'll just jump over here to the bounds theorem. Now, again, this is like the Descartes rule of signs. It seems complicated, but it's just synthetic division. So now what we're going to do is we're going to assume, at least in this case, that we have a real polynomial. And as far as WebAssign is concerned, they're always going to usually have that the leading coefficient is positive, even though you don't require that. It just makes bookkeeping a little bit easier. You can always multiply through by a -1 if that's not the case, and that doesn't change any zeros. So now what we're thinking of, say we did our synthetic and we were dividing by or testing a number that was positive, like we did the 3 or the 4. And when we look at the synthetic row, and it just contains non-negative numbers, that is, there are no negative numbers, they're either 0 or positive, then that's a red flag that says stop. Basically, if you try numbers larger than B, you're wasting your time, because that means you're going to add a list of numbers that are either 0 or positive and hope to get 0. That will never happen. So the first line is very intuitive and appeals to what we think about when we try to get zeros. You can't add a bunch of non-negative numbers and get 0 unless they're all 0. And that's not going to happen in what we're doing. Now for 2, when we look here, we're thinking, what's the other way? Say we're trying some negative numbers. Say we divide, or we're doing our rational zeros theorem and we're maybe testing -2 or something. And we're thinking, okay, do I need to keep trying? Do I need to try a number less than -2 if -2 doesn't work? Well, we have a little sign that tells us when we look at the synthetic row, if we get alternating non-negative, non-positive, and this can be in either order. If you start with non-negative, that would mean that the leading coefficient was positive. So that means you have an alternation in the entries. That is positive, negative, non-negative, non-positive. So that would be a red flag that says stop. Don't try any other rational zeros less than this. The idea is that this bounds all zeros, not even the rationals. So it helps you, like gives you even additional help with the rational zeros theorem, so you don't spend your time trying more numbers. I've seen cases where a student would try 5 or 6 numbers where the bounds theorem clearly told them to stop. And like I say, I think they felt like, well, I'm going to find this rational zero if it kills me. But just remember this, ladies and gentlemen, once these patterns occur in the synthetic row, you need to listen to them, because again, you need to heed them, because they will save you time. Now, what I want to do is do an example and then illustrate it with a simple problem like we did with Descartes. So let's do another example that illustrates the bounds theorem. Now remember, ladies and gentlemen, the bounds theorem is not extremely robust. I mean, you can't just say, oh, it's going to give me a perfect bound. It won't be a, supremum, like is the least upper bound or the greatest lower bound. It just gives you a benchmark. So don't expect it to be on the level of calculus. So for instance, say we had a polynomial that looked like this, and then we'll illustrate the bounds theorem with it. I think it's good to see it working with an example. You've already seen me use it with the synthetic division with the rational zeros theorem. So I just want to use now an illustration with a polynomial that we can easily factor. Now, when you look at this, this is going back to the type of example that I talked about at the beginning of the lecture. That is, if we have a quadratic form, we can try to factor this and save ourselves a little bit of time. So you can see that you've got a nice AC method going on here. So quadratic form, AC will be 4 times 9. But this is tailor-made for this, because now we know that's a 36 and we need a 37, so we can just use a -1 times the -36. That's really kind of cheap when you think about it, because it doesn't require much number theory. It's just saying that a negative times a negative is positive. So that's going to give us the 36 that we need. And then of course the sum of the Z and W is the -37. So that's a quick way to factor this polynomial just by the method of Professor Ron's AC lemma. So now we'll do 4x to the 4th minus 36x squared minus x squared plus a 9. So we wish all of them were this easy. Well, I mean, it's not really easy. We still have to think about what we're doing, but we're using techniques we're already familiar with. So now we can factor the 4x squared from each of these terms. So 4x squared, that will leave us an x squared minus a 9. And then, of course, we can do the same here. We can factor the negative 1. So again, quadratic form is our friend, and we see now that the x squared minus 9 multiplies the 4x squared and the negative 1. So this will give us, at least for now, x squared minus 9 times 4x squared minus a 1. Now, of course, these are differences of squares, but we can think about complete factorization, ladies and gentlemen, and go ahead and factor the 4, because we see now that that 4 is the leading coefficient. So factor this 4. So this will be 4. We'll go ahead and factor this difference of squares, x minus 3, x plus 3. Now, of course, this is an even function, so we see that our roots or zeros will be symmetrically distributed. That's even, clearly even by the even powers here. And then this will leave us an x squared minus a 1/4. Because if we factor the 4, we have to divide the 1 by 4, and then we can finish it off. So we got 4 times x minus 3, x plus 3. You can put in 2 negatives if you like. And we have x minus square root of 1/4 is 1/2, and then x plus 1/2. So this complete factorization was done via factorization, so to speak, the methods that we reviewed in the first week of class. So now when we look at the zeros, we have 3, negative 3, 1/2, and negative 1/2. So when you look at this, you're thinking, well, we've got complete factorization. All we need to do now is throw in some imaginary zeros, and we've covered all the bases. But what I want to show you here is, for instance, if you were doing some rational zeros theorem, and let's just look at it this way, and you were thinking, well, you know, do I need to keep moving with this? And I'll just say that, you know, we can we'll take some, like, maybe some easier numbers here, but what I want to do is, like, just take some numbers that are bounds here. Say I was not actually sticking so much to a list, but I was thinking I want to try maybe 4 and negative 4. Now here's what I'm looking at. 4 is an upper bound for 3, which is the largest positive zero. And negative 4 is a lower bound for negative 3, which is the smallest negative zero. So you're thinking those should exhibit the bounds theorem. So, and the reason I'm using it is because the numbers are easy and we've got a nice even function. So we have 4, 0, because we don't have a cube term, negative 37, 0, and then a 9. Of course, no x term, so we need a placeholder. So I'm going to say that I'm going to try the number 4 as a 0 and see if I get the jackpot. And if I don't, does it tell me to keep going or to give up and try something else? So I'm, again, illustrating what we have here. Bring the 4 down. 4 times 4, that's a 16. Now we have, in this case, we've got a 64. So 64 here, and we've got a negative 37 here. So that's a 7 and what, a 2. So that gives us a 27. And then we have 4 times the 27. So that's an 8, and a 8 plus a 2. So that's a 108, right? And well, it's looking pretty grim. And now 4, that's going to be a 2, a 3, a 432 plus a 9. So that's going to be a 441. Just add 10 and subtract 1. Okay, well, if I were thinking that going in this direction were good, I need to rethink. And I would expect this, because now this is what we're trying to illustrate, is you're doing the rational zeros theorem, because we could see that we could get a 9 out of this. So I'm showing you that if you tried 4, there would be no hope here. This basically says stop. Stop going in the direction greater than 4, because you have all non-negative entries. All non-negative entries. So even though, like I say, this is not a major calculus result, there's no way that you can add a bunch of positive numbers and ever get 0. So that's a waste of time. Now let's play devil's advocate and use the fact that this is even. So we're going to do a -4 here. Now, we know what goes down here. That's going to be 441. This is an even function, but I'm just kind of showing you that we expect that because this is an even function. So as we go on either side, we get the same output. So let's just see that the bounds theorem would tell us that anything less than this number would be a waste of time. So bring the 4. So it's going to be the negative of this, -16. And now we get the positive 64 minus the 37. So that's going to give us the 27. And then now here, we're going to get the negative of this number because of the -4. And then, of course, 108. Math is really so rewarding. It just lets you know everything before it's too late. And so now we're thinking, okay, we get the 432. Well, we know this is 441. We don't have to do it again. We know that's the answer. Now notice alternating, non-negative, non-positive, non-negative, non-positive. And so this is alternating. And so the bounds theorem says, don't try anything less than this because that's a lower bound for the negative zeros. And we know it is. We already know it is. But what I want you to see is that it's nice to have a really efficient illustration of this. So as you're working your problems and you try one of the lists, candidates from the list, and you see that this, either one of these situations is exhibited, then you stop because there's no reason to move forward. A number bigger than 4 would be a waste here. A number less than 4 would also be a waste here. And I will also tell you this, you could rig this to be a special case of that. So the idea that we're talking about all kinds of algebraic constructs here, this is basically the division algorithm with some basic constructs of function transformations. So there's so much power in the work that we do in this class. And of course, you can see how you could be spending quite a bit of time motivating all of this theoretically. That's good. That's neither good nor bad. It just depends what you like to do with your mathematics. But it's nice to know how things work, at least how things fit together, how we can take the rational zeros theorem and pair it up with the bounds theorem to make our work a little bit more efficient. And that's always a plus. Efficiency is good. Now, what I want to do is talk about some ideas having to do with imaginary zeros. Because at this point, we've exhausted the real zeros. We know what complete factorization is. And now we just need to say a little bit about zeros that aren't real. So first thing is this. We have fundamental theorem of algebra and complete factorization, which we've kind of beaten up. And the next result that I want to give you has to do with constructing polynomials and complex conjugate pairs. So here's a theorem. I'll just go ahead and write this one out. You can find these in the ebook like we did before, but I'll just change it up a little bit. I'll say let p of x be a real polynomial. Remember, we use the script r to say that we have a polynomial with real coefficients. And suppose suppose a plus bi is a 0. And we're assuming that the b is non-zero. That is, it has an imaginary part. So we have a real polynomial with a imaginary 0. Maybe it's square root 2 times I, or maybe it's 1 plus I. The imaginary part, the b, is non-zero, so we want an I in this. Then the conjugate, the complex conjugate, a minus bi is a 0, is a 0. What this is basically saying is p of a plus bi equals 0 is basically equivalent to p of a minus bi equals 0. If you have a real polynomial with an imaginary 0, the conjugate of that 0 is also a 0. So we get that for free. So that's why when we did the Descartes, we could never put for a real polynomial that there was one imaginary 0, because this theorem will not allow that. The quadratic formula, the plus or minus, gives us these complex conjugate zeros. And so this is a gift. So anytime you're dealing with a real polynomial, imaginary zeros must occur as complex conjugate pairs. So we can say imaginary zeros, just say it another way, imaginary zeros must occur as complex conjugate pairs. So that's something you learned about in in college algebra. Now, using the properties of conjugation, you can actually effect a very straightforward proof of this. It's not difficult. But what's nice, at least at this point, is that we always get an even number of imaginary zeros for real polynomials. We could never have 1 or 2. And if we did, the polynomial would have to have complex, well, it would be complex. This is complex also, but it would have to have i's in some of the coefficients with some imaginary coefficients. So again, any polynomial is complex. Any polynomial we write down as complex because the complex numbers include all numbers. Natural numbers, integers, fractions, square roots, you name it. The complex numbers also include the imaginary numbers. So we can call any polynomial complex. But if we want to notate the point that it actually has an I in it, we have to say imaginary, okay? And remember, I is the square root of -1. And of course, I squared equals -1. So that's kind of a little recipe box that you need to remember about that. Now, another thing that can be convenient, remember we built some polynomials last week? Here's a little lemma that can help us construct quadratic factors for the imaginary zeros. And I'll show it to you, it's very easy. So let P of X be a real polynomial, just like we have up here, and suppose a plus bi is a 0. And again, we're assuming that b is not equal to 0. Now, the quadratic factor that p must now have will give us these zeros. So P of X has the quadratic factor as follows: x squared minus 2ax plus a squared plus b squared. That means if you tell me that a particular real polynomial has to have that 0, say 2 plus I, then I fill in the a and the b here to construct the quadratic polynomial that provides these as zeros. Now, of course, you could multiply it out, but that's why you prove this result, so you don't have to multiply things out and make 2 or 3 mistakes. So the idea is, what is this saying? X minus A plus BI times X minus A minus BI, if we're thinking about the factor theorem, is actually this polynomial. So that would be the proof right there. So why have to do this every time? Just fill this in. So now you've got a little result here that gives you the quadratic factor. So let's use some of these. And I've got some WebAssign problems here. So first we want to do a factorization. Then we want to build a polynomial using our new little tricks here. And they are tricks, even though they're theorems, we think of them as very handy tricks. So let's do a complete factorization of the following polynomial. So we have P of X equals X cubed plus 3X squared plus 6X. Now, if I look at this polynomial, somebody answer this, true or false? P has exactly 2 zeros, true or false? Don't be shy. P has exactly 2 zeros.
False.
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 How
Wouldn't it have 3?
How many does it have?
3.
Absolutely. Good, Catherine. Good, Brian. So can you give me one that's obvious? Well, let me just say this. I'm gonna factor what? The X.
Would it be 0, 6?
Well, what's an obvious 0 here, Brian? 0.
One would be 0, and the other one would be positive 6.
Well, almost. So we need to factor this, right, to figure out
yeah.
if we have 0. But we still see that X equals 0 is a 0. So excellent. So this implies we can at least say, all right, one of the zeros, as Brian has said, is 0, right? Now, are we home free? True. I want you all to answer another question, and not Brian or Catherine, because you all answer all the questions. Now that's good. I know you love math. Look at this part here. What am I going to say? I'm going to say the X squared plus 3X plus 6 requires the use of the rational zeros theorem. True or false? Brian, you can answer if you want. The X squared plus 3X plus 6 requires the use of the rational zeros theorem.
True.
It could be true, but is there an easier way to do it?
Would it be just factoring it?
Factoring it, yeah. So, true or false? If a polynomial, if a quadratic has an imaginary 0, it has an imaginary 0, then you can use the rational zeros theorem to find it. True or false? Let me say that one more time. If a quadratic polynomial has an imaginary 0, then you can use the rational zeros theorem to find it. True or false? This is a trick question.
True.
So what's the answer?
It's true.
Well, is it
Isn't it the quadratic equation?
Is an imaginary 0 a rational number?
No.
No.
So what's the answer?
False.
False. Okay, I'm trying to trick you all, but you know I'm doing it in good spirit. Okay, now look, everybody. This is quadratic. So now what we want to use is our knowledge of the quadratic equation. Now, if you look at this and we try AC.
It's positive 3, negative 2.
Okay, so if I did that, can I rewrite this in a way to get a 3? Is that possible?
Yes, it's positive 3, negative 2. Wait, hold on.
Now that's a good try, but I don't think we're gonna get, then that will make that negative, wouldn't it?
No.
So what are we gonna write here? Is this Maricela?
No, it was Samantha.
Oh, hey, Samantha, can I make this work with AC? What do you think? Yes or no?
No.
No, I agree. No. Okay, so Samantha, what do I do now?
You go to your other possible zeros.
So I go to quadratic formula, right?
Yeah, you would have to.
So we're saying no rational zeros. Remember, if AC lemma works, I have a rational zero. And Samantha clearly said here that there aren't any, and I completely agree with her. So now notice we want to look at the discriminant, okay? Now, let me just write this down. A is what?
1,
B is what?
3,
3.
And C is what?
6.
Excellent. Okay, so let's fill it in. So we get 3 squared minus 4 times 1 times 6. Now, of course, you know I factor everything to death, but we don't have to. These numbers are easy. So we have 9 minus 24, and that'll give us a negative 15. What does that say?
It's going to be imaginary.
Absolutely. This says less than 0, so this implies 2 complex conjugate zeros. Now, I know you know this, ladies and gentlemen. This is review, but this is rusty. So the complete factorization says we can always completely factor a polynomial, but we don't really know what the quality of the zeros is going to be until we investigate further. So now we have x equals, so the opposite of b, negative 3, plus or minus the square root of negative 15 divided by 2a, which is 2. Now, of course, WebAssign would appreciate if we write the square root of negative 15 with the I. So remember, this would be negative 3 plus or minus the square root of 15 times I. Absolutely, divided by 2. Now, I'm going to tell you something that should make you very happy. WebAssign does not care if you don't write this as an A plus a BI form. They don't care. That's why I like WebAssign. WebAssign is smarter than we are. So you can leave your zeros in this fraction form. So now I'm going to go up here and I'm going to say negative 3 plus square root 15 I over 2. And I'm going to write negative 3 minus square root 15 I over 2. I have all my zeros. We have all our zeros. And now we're ready for complete factorization. Now, let me just tell you this. If you keep your complex number in this fraction form, it's real easy to type it into WebAssign with complete factorization. So now we have P of X. We've got a 1 out front. So we have, I'm going to beat this to death, X minus 0. That's just X, but just put the 0 to humor me. And then we have X minus, write the fraction, negative 3 plus square root 15I over 2. So if you write it as the fraction, it's all clean and you get your C2, you get X minus C2. And now we do X minus C3, negative 3 minus square root 15 I over 2, like that. So this is what I did when I was looking at your WebAssign. They are very flexible. So when you do this, you get your C1, so we can say that's the 1. So this is the A, X minus C1, X minus C2, and X minus C3. We should always be able to do this. And I know, ladies and gentlemen, I've been kind of focusing on writing it this way because this method is very useful when you get to calculus. We know when we do the inequalities, if we're doing a sign test, if we have it really cleanly written out where we can see the 0 and the X, then we can easily test the sign. And so this complete factorization technique is something you will use quite often when you do differentiation and optimization in Calculus 1. And it's a lot of fun. And it can be fun because you can do this. So let me just kind of recap here. We approach this just like we've done all the other problems. The thing is that sometimes we don't notice that we have a freebie here. The constant term is 0. So we factor the x and we have a free 0 right there. And then we've reduced to quadratic. And that's why I was kind of asking all of you all saying, okay, do I need rational zeros? What do I do? Once we reduce to the quadratic, we pull out all of our artillery for the quadratic. We think, well, let's try to factor it. That didn't work. So we do discriminant, and then test the discriminant. That gives us the complex conjugate, and then finish it off. So all we're doing today is putting together all of these different pieces to make what we do a little bit more efficient. We haven't learned that many new ideas. We're just thinking, okay, we don't want to do rational zeros all day long by checking numbers that would never work. And then we don't want to miss freebies. Lots of times when we're working, you're working on a test, you're focused and all that. You know, it's easy to do a problem less efficiently, but at the end of the day, who cares? As long as you do it correctly, that's all that counts. But I do want you to think as you're doing your homework for ways to make what you do as efficient as possible. Now, I want to just build a polynomial now that we kind of have an idea of what it means when we have imaginary zeros. So I want us to build this, and this will be very simple for you. So build Q of X. And here's what I want Q of X. WebAssign says we want the degree of Q to be 3, and we want Q to be an integer polynomial. So we want, integers, no imaginaries, no square roots, no fractions, all integer coefficients. And we want the following zeros. We want a 3 and a 5 odd. Okay. Now, we're thinking, what's this mean? Okay, we get to use our little lemma. So we've got our 0, and we have the factor right here. Okay, so for the 0, 3, what's the factor? X minus what?
3.
X minus what?
3.
3, good. Okay, now what about 5i? Do we do X minus 5i? Well, that wouldn't work. Why would that not work? Because we need
Because you have to get the other one, because there's 2 of them.
Right, but we need integer, right? We need integer
Yes.
coefficients. Is 5i an integer?
No, sir.
No.
Absolutely.
Imaginary.
Okay, so help me out. What's A here? What's A in this imaginary number? What's A?
5.
Well, A is 0. Remember, A plus BI. What's B?
5.
Is a 5.
B is 5. Okay, so now we write it down. So remember, this is x squared minus 2ax plus a squared plus b squared. Of course, you can write it out, but if we fill in the a and the b, what do we get? Get x squared plus what? That's 0.
Minus
That's
0.
0.
0
What's
plus
b
5.
squared?
25.
Good. That's it right there. Now, you probably could have figured this out without looking at this, but of course, if the a is non-zero, then this is very handy. So I want you to know how to use this. So now, if I multiply these two, am I going to have that degree? Absolutely, because that's degree 2, and that's what degree?
3. 1.
1. Okay, so the 1 plus the 2 would give us the 3, so we're good to go. So now we're like, let Q of X equal X minus 3 times x squared plus 25. Now, of course, WebAssign may not be mad at you if you leave it like this, but it's good to just write it in descending order. So let's just go ahead and practice. So multiply by x cubed plus 25x, and negative 3x squared minus 75. So if we write it in descending order, we get x cubed minus 3x squared plus 25x minus 75. So I want you just to see that this is exactly the same as we've done before. Actually, it was less restrictive because we didn't demand that we have a particular constant term. But notice, because we have this imaginary 0 and we want a quadratic, we want an integer polynomial, we can't live with x minus 5i. We have to go to the quadratic. So remember, this is the corresponding quadratic factor. This always works. You should verify this. You should multiply that equation out those factors out that I wrote on the previous page to verify this. You just have to use that I squared is -1. And it's very simple. The thing about this is that it's convenient and it's easy to remember. And so it gives you a nice quick way to build a polynomial when you have imaginary zeros. So main thing, ladies and gentlemen, is complete factorization. Complete factorization. Now, if we think about this, we're thinking we already have complete factorization because it was given that way. But if we just wanted to belabor the obvious, we'd say x minus 3, x minus 5i, and then x minus -5i. And then you're thinking, wow, that's complete factorization. But you see here that this is a polynomial with imaginary coefficients because of the 5i and this. Because if the polynomial, if the requirements say you can't do this, we have to keep it integer, we'll do this. But this will be complete factorization in terms of the fundamental theorem of algebra, which is also good. So the thing is, and I'll say this over and over and over and over, answer the question. If they ask you to write a polynomial that's integer, then this is what we need, okay? Make sure that all the coefficients are integers. If they ask for complete factorization, right here. Even though that's obvious, it's right here. So please be careful that when you work these problems that you pay attention to repetitions. We count the repetitions as zeros. Like if we've got a repetition or multiplicity of 3, then that counts as 3 zeros. So don't disregard that. That's how the theory is built. Now, I have an example here that I just want to share with you. It kind of snuck its way into WebAssign, and a student who's in one of my online classes that doesn't meet on a schedule, he came to office hours yesterday and said, Professor Ron, how do you do this problem? And I said, oh man, that says use a graphing calculator. And I said, sometimes when WebAssign mentions the graphing calculator, it's really bogus, you don't need it. But when I looked at this problem, I said, well, Luis, I think you do need it, but I went ahead and said, I'm gonna share this with my students so that when you see it, you don't just, look at it and shake your head. Now, this was actually what I wrote up yesterday during the problem session. And then after it was over, I did some calculus here that I'm gonna share it with you. So this is a problem where WebAssign would say, okay, use some device that has some graphing capabilities that would allow you to approximate a 0, because this 0 is not something that you could actually find with the standard methods. So let me just go over what the problem was. And Rose, here I wrote extra problem. I don't know that it's extra, it's in your web assignment. And I used the numbers in his problem. We had an area, we have this parcel of land which has a dimension X here, and the diagonal has dimension X plus 10. This is a rectangle. Has area 2,000 square feet. And then it said the dimensions of land correct to the nearest foot. So that would mean whatever you would get for the dimensions, you'd round to the nearest foot. Okay, so when I looked at this problem, I said, this is still a good problem. Let's just work it and see what we can do with it. So you've got your right angle here. So ladies and gentlemen, that means that you can apply the Pythagorean theorem. So we will just assign this dimension, the width, if you will, to be y, or you can use your favorite letter. And then of course we have a right triangle. So we'll have x squared is a leg, y squared is a leg. That is, we square these, add them, and that's equal to the square of the hypotenuse, which we have here. And then we just apply our binomial theorem, our identity. This will be x squared, and then we have 2 times x times 10, which is 20x, and then 100. And so now we notice that the x squared is absorbed, and then we're left with y squared is equal to 20x plus 100. Now I factored it here, but that really didn't turn out to be the best idea. I went back to the regular notation here because I figured out that they want us to create a polynomial. But you're thinking, what did I do here? Okay, well, ladies and gentlemen, this is square root property. That is, we have something squared is equal to a real expression. So we have y is plus or minus the square root of that expression. And so since y will be corresponding to a non-negative quantity, we will select the positive square root. So we get y is the square root of 20x plus 100, or if you wanted to factor it as a waste of time like I did, you could do it. So now, how does this help us out? Okay, well, then I asked the attendees, I said, well, how do we find the area of a rectangle? Well, you know, they knew that, length times width. So the area, which we could just call A of x, let me move this up, will just be x times y. Well, the x is x, but now the y is just this expression here, the positive. So we have the square root of 20x plus 100. But that is equal to the area here that's given, 2,000 square feet. So we have this expression equals 2,000. Now, this is where you think, say you're in a physics class or in an engineering class, and you're thinking, well, I need to rework this into a form that has something to do with what we've been studying. And so that's where it occurred to me. I said, okay, this is in your real polynomial section. Let's just square the equation and create a polynomial. So they were fine with that, but then that's when they thought, man, this was hard. I said, well, yeah, it's a hard problem. It's different, but it's what you do in calculus. So when we square everything, we get x squared, and then of course we square the radical, we are relieved of the radical, so we get 20x plus 100. And then this is where I did my little symbolic computation, which I love to do. This is squaring, it's like, well, newsflash, it's like I say, I'll factor. If someone says they're having an issue with something, I said, did you try factoring? And they're like, oh, is that a math joke? I'm like, yes, of course it is. So the thing is that we square 2 times 1,000. So this gives us 4 times 1,000 squared. So what I did is I thought, okay, we're going to need to move this over and then divide by the 20. So we get a 20x cubed and then a 100x squared when we multiply this side. So I went ahead and redid this. This 4 times 10 I wrote as a 2 times a 20. And that leaves the 100 behind and the 1,000 as we have right here. So I let the algebra do the work. You don't do this, you just become lazy. And so now when you divide by 20, you get x cubed, you get 5x squared, and then of course this leaves behind the 2 times the 100, 200 times 1,000, which is 200,000. And you're thinking, wow, look at this. That's the polynomial. And you're thinking, oh, joy, joy, Professor Ron. I guess I'm just going to look at all the factors of 200,000 and apply the rational zeros theorem. Well, the answer to that is no, and then no. What you have here is a situation where you're thinking, well, I could try to factor this, but it really doesn't, you know, I told him, I said, if we were trying, this is what I did during the session right here. I said, if we were trying to do AC, I'd start doing this. I said, and so I showed them about that. And then they said, well, wait a minute, this is cubic, it's not quadratic. So then I said, we need to use some calculus. Now, before I do that, this is what I did. This is actually, I did this during the session, but when they left, I thought, well, tomorrow I'll share this calculus with them. The thing is that if you try to graph this, it's going to look like this, but you need calculus to do it. When you take the derivative of the polynomial here, let me show you. When you take the derivative of this polynomial, you get this, and of course we factor it to death, and we get the two zeros, 0 and -2/3, or -10/3. Now, these are horizontal tangents, which both occur below the x-axis. The y-intercept is -200,000. And so there's exactly one real zero here. There's only one real zero, but note it's not 1-to-1. This is not a 1-to-1 function. And so at that point, that's when I thought, well, that's probably what would have made them feel better. So at this point, I used a Newton method calculation, which I found online, because this is something I would have to teach you in calculus and it would make no sense at all. So I told them, aside from just doing some checking, I said, I'm going to go on and I'm going to use Newton's method, which I'll teach you in Calculus 1. I wrote numeric method, and I give an approximation of 56.86. Then WebAssign says, okay, round to the nearest whole number, which is 57. And then I said, remember what y is, it's right here. This part, this radical right here. So I go in here and substitute 56.86 for x to get an approximation here. Hit it with a 20, add 100, square root, and get approximately, here I use my Google calculator. And I tried to write this, I was scribbling it kind of fast, so when I got ready for lecture, I made it look nicer. So you think I was just completely rogue. And so I got 35.17, and then round to nearest integer. So now the parcel of land has approximate dimensions 35 feet by 57 feet. But again, let me just focus on this here. When you think about the cheap graphs that we did before, we did not have access to easy zeros when you look at this. We don't have easy zeros. So I used the calculus here to get a reasonable graph that verifies that there's only one solution, so that they would not be searching all over the place to find a solution and then try to figure out which one was working. So when you see this problem, here's what you're going to see. This is how the answer will have to be stated, but you'll have a little picture that looks like this. And you will do it the same thing here. And I want you to generate this. And then you can send me a message on WebAssign, help me, Professor Ron. I don't know what to do with this. You had to use calculus. Now you can either, I can help you with it, or you can find a friend that has a fancy calculator, or go online. But I would want you to do this at least. I want you to go to this point, and then you can estimate. You can estimate and then go to a numeric method that you can find online, or just use a graphing calculator to get this. I think this is a good problem. And the student, when the student asked me about it, I thought to myself, this would be a nice introduction to the methods of calculus. And so, like I said before, this is where Newton and Leibniz introduced a method that allows us to get more information about differentiable functions in a manner that is useful. So when you look at this picture here, ladies and gentlemen, this reminds us of what we've been doing in 3.1 and 3.2, but this required the use of the derivative. And again, you're noticing here, when I graph this, we see that the function here is above the x-axis where the function increases. Here it's below, the function decreases, and then it increases. So the sign convention that we have used so often with inequalities will be the same thing that you will use when you analyze derivatives in calculus. So I didn't want you to get to this problem and think that I just pushed you off a cliff. I just wanted to, I thought about this and I said, you know, I'm just going to leave it there and let them have a good time with it. So don't worry about the fact that you don't get it perfectly or whatever. Just try it and use it as a culture problem. So a lot of times when we're working problems that go beyond the class, I call this a culture problem because it's of interest and it's where we're headed. So we're going to learn some trigonometry. We're going to learn some more about exponents and logs. We're going to learn about conic sections. We're going to learn about sequences and binomial theorem and induction. So when you get to calculus 1, you'll hit the ground running. So this kind of concludes the information that we need for the theory of equations. What we're going to do on Thursday is talk about rational functions and how we graph them. So we'll talk about the asymptotes that we have where we deal with vertical and horizontal asymptotes, graphing rational functions, understanding rational functions, and then I may just say a little bit about, even though I told you I probably wouldn't do much, I may just throw in an inequality to remind you about the BV technique. But once we finish that, ladies and gentlemen, we will now proceed to chapter 4 and review exponential and logarithmic functions and add some new ideas. But again, we will be like we are right now. We're kind of at the cusp. We need some calculus. So we're going to do everything we can do devoid of the calculus. And when we get to calculus, hopefully we'll be able to fill in all the details that we can't do at this point. Okay? Well, I appreciate your attendance today. You all, I appreciate your support by answering questions. I know that sometimes it can be a little bit nerve-wracking, but it is a pleasure to have you all participate. And so get some rest and stay dry. Hopefully the rain will subside. I can't tell that it's raining right now. I think it's about to stop. I'm keeping my fingers crossed. But have a great rest of the day, and we'll see you all back on Thursday. If not, I'll see you at the conference hours. Have a good day.
Thank you, you too. Bye.
Thank you,
Bye. Bye, everyone.